Alright, here's a ratio test problem. This is 14B from the test review. So you have the answers to that, but I'll work it out step by step here. It is 2 to the n squared over 2n factorial. Note that this is unnecessary to have these parentheses on the n squared. It's exactly equal to the same thing as 2 to the n squared over 2n factorial n equals 1 to infinity. It does need the parentheses around the 2n factorial. Order of operations on the top, n squared happens first because it's higher on the exponential tower. But for factorial happens before multiplying by a number. So if I want the factorial to be on that whole thing, I have to put parentheses around it. All right, so for the ratio test, the limit as n goes to infinity of the absolute values, and now I plug in n plus 1 for each of the n's. So I'll have 2 to the n plus 1. Now I do need to make sure that's n plus 1 in parentheses squared. Whenever you substitute in for a variable, no matter what you're doing, you always have to put parentheses around it to make sure that you substituted in for that whole variable. So it's n plus 1 quantity squared. And I needed parentheses around those too because it's 2 times n plus 1. And I need parentheses around that whole thing because the factorial happens after the multiplication by 2. Then a copy of the original. However, it's divided by the original, so I just multiplied it by the reciprocal, flipped it. All right, now for a bunch of algebra, I can reduce it or simplify it as much as I can. I noticed that there are no minuses in this original problem, so the absolute value will just leave it exactly the way it is. Everything is a positive number there multiplied together. So I don't need the absolute value bars anymore. And now I can expand some of those parenthesized expressions. So for instance, 2 to the n plus 1 squared will be 2 to the n squared plus 2n plus 1. That kind of might be good to have parentheses there just to see it, since it's all in the power. That was doing FOIL on n plus 1 squared. And then I'll have 2n factorial. And then underneath, make that a 2n plus 2 factorial. Multiplying through the parentheses. And 2 to the n squared. Alright, so now I have some things I can cancel, since I'll try to cancel some of the powers and some of the factorials. For the powers, this is n squared plus 2n plus 1 and n squared. So the 2 to the n squareds cancel. And I'm left with just 2 to the 2n plus 1. And for the factorial, I'd like to do the trick where I start working out the factorial, expanding it, because it's what it means is start with what you see, multiply by 1 less, by 1 less, and then I'll be able to cancel with 2n factorial. But this time, I'm going to have to pull out 2 pieces, because the first time I write down 2n plus 2, Then I write down 2n plus 1 because it's 1 less. And then finally I get to 2n. And I can just say that keeps going forever. Well, not forever. Just down to 1. And so that's the same as 2n factorial. I canceled the 2n squared with the 2 to the n squared. 2 to the n squared on top and on bottom. Now I can cancel the 2n factorial on top and on bottom. So I'm left with 2 to the 2n plus 1 divided by 2n plus 2 times 2n plus 1. And it's back down to basically as simple as it can get there. And now it's time for Calc 1 limit taking. I guess I'll FOIL out that denominator so I can see it better. That 4n squared plus 6n plus 2. So if I take the limit of that as n goes to infinity, at first I get 2 to the infinity divided by infinity. So it's infinity over infinity. So I'm getting infinity over infinity here, so I'm going to use L'Hopital's rule. And so I'll take the derivative on top and on bottom. And take the limit as n goes to infinity of that. So separate derivatives on top and bottom. The bottom derivative is easy. That one's 8n plus 6. But on top, that's an exponential function. So I have to remember the rules for that. When you have an exponential function, it's like e to the x, so it's always its own derivative. But then if it's not e as a base, you have to multiply by the log of the base. So derivative would be 2 to the 2n plus 1 natural log of 2 times 2. So that's the copy of the original, 2 to the 2n plus 1, natural log of the base, natural log of 2, and then that last 2 is because of the chain rule. Since it's a 2n plus 1, I have to multiply by the derivative of the inside function, which is 2 again. Yep. Unfortunately, I'm still getting infinity over infinity. So I need more L'Hopital's. Let's abbreviate that. I need to take the derivative on top and bottom again. Again, the bottom derivative is easy. That's just going to be an 8. The top derivative, I have to keep all those constant multipliers, natural log of 2 and 2. But the derivative of 2 to the 2n plus 1 is going to be the same thing I did already. So I'll have 2 to the 2n plus 1. I'll have a natural log of 2. Well, I'm going to have another one. So I'll just go ahead and square that one because it's natural log of 2 times natural log of 2. And I'll have 2 times 2 again, so times 4. And now I'm getting an answer which is infinity on top because it's 2 to the infinity and 8 on the bottom. So I got an answer of infinity. And let's see, the ratio test just says as long as you get something larger than 1, you know that it diverges. So basically what we figured out here is that 2 to the n squared gets big faster than 2n quantity factorial. And by taking a L'Hopital's rule on top and bottom a couple of times, we can see that it heads to infinity. So the whole sum diverges.